Hello, welcome to Lecture 16. In this lecture, we're going to carry on with our discussion of induced charges on conductors. Then we'll also talk about our last electrical property of a conductor, which is to find the electric field just outside of a conductor. Then if we have time, we'll move on to the next chapter. Our discussion of placing a point charge inside the cavity of a charged conductor is much like the discussion of a point charge inside an uncharged conductor. So let's start by saying that our conductor has charge plus Q. We know that the excess charge of a conductor is going to spread on the surface. We haven't put anything in the cavity yet. So that charge plus Q will spread to the outer surface of the conductor. Because all of those charges repel each other and they want to spread apart. So then next we'll place a point charge of little q in the cavity. So plus Q. That's a little point charge. Well, now what happens in our conductor is still that the movable negative charge in the conductor will get drawn to the inner surface. So we'll get negative charge drawn to the inner surface. If we want to figure out how much is that charge, what we would do is draw a Gaussian surface inside the conductor. So that's a Gaussian surface. We'd say that the net electric flux is equal to the integral of E dot dA equals Q enclosed over epsilon naught. The electric field is equal to 0 because it's inside a conductor. So Q enclosed would be however much charge is on the inner surface. So charge on the inner surface plus our point charge has to be equal to 0. So the charge on the inner surface would be negative Q. Which makes sense. If we have plus Q here, it's going to attract negative Q here. If you want to think about it canceling out, that's kind of okay, but the amount of charge is going to be attracted to this charge. And when the net charge inside our Gaussian surface here, when the net charge is equal to 0, that's how we get an electric field of 0 inside of our conductor. That's not the whole story. This point charge doesn't just attract the negative charge, it also pushes extra positive charge away. So some positive charge will get pushed to the outer surface. If we want to figure out how much charge is on the outer surface, what we would remember is that Q of the conductor was given as plus Q, but Q of the conductor is also how much charge is on the outer surface, QO, plus however much charge is on the inner surface. So the charge on that outer surface would be the net charge. Take away the charge on the inner surface, so Q minus Q, be Q plus Q. So however much positive charge is in here, we'll push that much charge to the outer surface. Okay, so this was all in very general terms. Let's move on and do an example next. Oh wait, let's just talk about electric field for a tiny second before we move on. So inside this cavity, there is a charge, so we will get electric field inside this cavity. Inside the conductor, there's no electric field here, and once we're outside, we do get electric field again. So next we'll move on and do an example. So for an example, let's say that we have a point charge Q, that's the dark gray one, and it's inside the cavity of a conducting shell, so we've got our spherical symmetry, and our conductor has a net charge of plus 2Q. What are the induced charges on the inner surface of the shell, so this part here, and the outer surface? So we've got plus Q right here, That's our point charge, and we know that Q of the conductor equals plus 2Q, and our point charge is just plain plus Q. We can even label this over here, Q conductor equals plus 2Q. We know that we're going to get some induced charges. This positive charge plus Q here is going to add some negative charge to the inner surface. It's going to pull some negative charge to the inner surface. Let's call that charge Qi. And we also know that it's going to affect the charge on the outer surface. Let's call that Qo. So we're asked, what is the charge on the inner surface and what is the charge on the outer surface? If we want to figure out the charge, let's use a piece of information that we know. And the piece of information that we know is that the electric field inside a conductor equals 0. So let's draw a Gaussian surface. Gaussian surface in the conductor. And we're picking it there because we know that the electric field is 0 there. So that's what we mean by pick a Gaussian surface where it's useful. It's useful because we know the electric field equals 0. We'll write Gauss's law. The net electric flux is the integral of the electric field over the area of that Gaussian surface. That's equal to Q enclosed divided by epsilon naught. Q enclosed is net charge inside the Gaussian surface. So now our electric field equals 0, which means that our Q enclosed must be equal to 0. And Q enclosed equals whatever charge is inside our Gaussian surface. What charge is inside this blue dashed line? Well, the only kinds of charge we have inside this dashed line is whatever charge is on the inner surface and this point charge. None of the other charge is inside this circle. Everything else is outside, so it doesn't count. Only the stuff inside counts. So equals Q on the inner surface plus the point charge plus Q. That tells us that 0 equals Qi plus Q, which tells us that Q on the inner surface equals negative Q. It's kind of a familiar result by now, but it's still useful to go through the process. Okay, so that's the charge on the inner surface. Qi equals negative Q. What about the charge on the outer surface? Well, let's go to the fact that we know that the total charge on the conductor, wherever it's sitting, the total charge is equal to 2Q. So on conductor, Q of the conductor equals plus 2Q. And whatever charge is on the conductor is either on the outer surface, QO, or on the inner surface, QI. So this total charge of 2Q is either on the outer surface or it's on the inner surface. So to get the total charge, Q of the conductor, that's Q of the outer surface plus Q of the inner surface. So that tells us that 2Q is equal to Q of the inner surface plus Q of the outer surface. Q of the outer surface then is 2Q minus Q of the inner surface equals 3Q. Because Q of the inner surface is minus Q. So 2Q minus Q is 2Q plus Q equals 3Q. So charge on the outer surface, QO equals plus 3Q. And you'll see when you add those guys up, you do get your 2Q. Okay, next part, and I'm going to spill over onto the next slide to do this, is let's sketch the electric field. The next part of the problem is to sketch the electric field. So there are 3 areas to sketch the electric field: in the cavity where the point charge is sitting, in the conductor itself, and outside the conductor, so outside everything. So we've got in the cavity, conductor, and outside. For in the cavity, let's look at what we have in the cavity. The only thing we have in the cavity is a point charge, and we know what the electric field looks like around a point charge. The electric field comes out of the positive charge and spreads out radially. I'm going to draw 8 lines just because it's nice and symmetric. Okay, what's next? Well, what about in the cavity, or in the conductor, I'm sorry. So let's label what we had in our cavity. So in the cavity, E equals KQ over R squared. In the conductor, of course, the electric field is equal to 0. So KQ over R squared, 0. Outside, here's where we're going to have to figure this out, and we're going to use Gauss's law. Gauss's law. So let's draw a Gaussian surface. Let's pick it to be useful and symmetric. We have spherical charge, so I'm going to pick a spherical Gaussian surface. I want to know something about the electric field outside, so I'm going to draw my Gaussian surface outside. I'm going to write down Gauss's law, which says that the net electric flux through my Gaussian surface is the integral of E dot dA equals Q enclosed over epsilon naught. For the integral of E dot dA, I'm not going to go through this again because we've done it so many times, but I'm going to say show steps. So if this were on a test, you would show these steps problems, dot, dot, dot. That turns out to be E times 4 pi R squared equals Q enclosed. I wrote a lowercase q up here. Maybe I'll just put that into my uppercase q so I'm consistent with notation. Q enclosed over epsilon naught. So E is 1 over 4 pi epsilon naught times Q enclosed over R squared. E equals K times Q enclosed over R squared. So the big question is, what is Q enclosed? Well, Q enclosed is however much charge is on this Gaussian surface. So it's all of the charge on the conductor plus the point charge, because that's how much charge is inside this purple dotted line. So equals K times 2Q plus Q divided by R squared equals K times 3Q over R squared. This is a pretty important result. So my electric field outside, let's write down that expression. E equals 3 times K times Q over R squared. My electric field out here depends on 3Q. Inside, it depends on Q. Remember, back when we talked about electric field lines, we said that the number of electric field lines is proportional to the amount of charge. So the electric field through our Gaussian surface here looks like the electric field of a point charge where the size of the charge is 3Q when we're out here. So there are going to be 3 times as many electric field lines. So if I have a line here, I'm going to have to add 2 more lines going radially outwards. One here, a line here, and then 2 in between. Okay, as usual, I don't draw the best, but hopefully you're getting the idea. So there have to be 3 times as many lines because there's 3 times as much charge. So as we go through the course, you'll see that the material does tend to continue building on itself. Okay, so 3 times as many lines. Because it's 3 times the charge. 3 times as many lines as that of inside the cavity. So there's our sketch of the electric field. For this example, we have a point charge of minus 2Q. So that's negative minus 2Q. It's placed within an irregularly shaped cavity, so it's kind of a jagged edge here, of a conductor holding excess charge of minus 3Q. So this is our conducting part. Q of the conductor equals minus 3Q. And our question is, what is the net charge on the inner and outer surface of the conductor? So what we know is because we have a point charge in the cavity, it's going to draw some charge to the inner surface of the cavity, that's this part, and we'll also have charge spread to the outer surface of the cavity. Let's label those 2 charges. Q of the inner surface, we'd like to find that, and Q of the outer surface, we'd like to find that. So the first thing we'll do is let's draw a Gaussian surface in a place that's going to be useful. I'm going to pick inside the conductor. The reason that's useful is because I know the electric field in there is equal to 0. Now for my shape of my Gaussian surface, I'm just picking a blob. I can't really decide what the symmetry is because everything is such an odd shape, so I'm just going to pick an odd shape for my surface. So there's my Gaussian surface, and it is inside the conductor. That's still useful because inside the conductor my electric field is equal to 0. Now I'm going to write Gauss's law. The net electric flux is equal to the integral of E dot dA equals Q enclosed over epsilon naught. This part is 0 because the electric field is 0. That tells me that Q enclosed, so the net amount of charge inside the Gaussian surface must be 0. And the net amount of charge inside the Gaussian surface must be whatever is spread to this inner surface and the point charge. So Q of the inner surface plus the point charge minus 2Q. So 0 equals Qi minus 2Q. So Qi equals plus 2Q. The point charge draws equal and opposite charge to the inner surface. Okay, for on the conductor, we know that the net charge of the conductor equals minus 3Q. And we know that the net charge of the conductor is spread on the two surfaces. So it's whatever's on the outer surface plus whatever's on the inner surface. So let's put those two guides together. Minus 3Q equals Qi plus Qo. Qo equals minus 3Q minus Qi equals minus 3Q minus 2Q equals minus 5Q. Oops, I wrote a G instead of a Q. Minus 5Q. So that's how much charge is on the outer surface. So we get plus 2Q to the inner surface, which leaves minus 5Q on the outer surface. This next one I'm going to leave for a homework example. It's pretty straightforward, so I'm not going to do a video, but I will post the solutions with the notes.